In this video, we will be learning about formula mass and molar mass. Formula mass is the sum of the atomic masses for all the atoms within a compound. The units for formula mass are the atomic mass units, or AMU. Formula mass is a generic term that can be applied to both ionic and molecular compounds. You may hear the term molecular mass, which is technically just for molecular compounds, but it is calculated the same way as formula mass. For our purposes, these terms are calculated the same way, although formula mass is the more general term. Let's work through two examples of calculating formula mass. First, consider the hydrate with the chemical formula Cu parentheses ClO4 close parentheses 2 dot 6H2O. We need to interpret the chemical formula to determine how many of each element is present. Since there is no subscript after the copper, we have one copper atom. The ClO4 is inside parentheses with a subscript 2 outside the parentheses. This subscript applies to every element inside the parentheses, giving us 2 chlorine atoms and 8 oxygen atoms. Because this is a hydrate, we also need to include the 6 water molecules. The coefficient 6 tells us that there are 6 water molecules. Each water molecule contains 2 hydrogen atoms and 1 oxygen atom, giving us 12 hydrogen atoms and an additional 6 oxygen atoms. Next, we use the periodic table to find the atomic mass of each element. We multiply the number of each atom by its average atomic mass, and then we add all of the masses together. Adding the mass of 1 copper, 2 chlorine atoms, 8 oxygen atoms, 12 hydrogen atoms, and the additional 6 oxygen atoms gives us a total formula mass of 370.55 AMU. Next, let's calculate the formula mass of C6H6. This molecule contains 6 carbon atoms and 6 hydrogen atoms. We multiply the 6 by the atomic mass of carbon and the 6 here for hydrogen by the atomic mass for hydrogen. This gives us a total formula mass of 78.11 atomic mass units. Depending on the precision of the periodic table that you are using, your final answer may differ slightly in the digits after the decimal point. This is acceptable. However, do not round your formula mass values. Always keep at least 2 digits after the decimal point. Here's a practice problem. Calculate the formula mass of each of the following compounds: N2O5, magnesium nitrate, and sulfur hexafluoride. For the first compound, N2O5, the formula tells us that we have 2 nitrogen atoms and 5 oxygen atoms. Using the atomic masses from the periodic table for nitrogen and oxygen, this gives us a formula mass of 108.02 AMU. For our second compound, magnesium nitrate, we first need to determine the chemical formula from the name. This is an ionic compound because it contains a metal combined with a polyatomic anion. Nitrate is NO3 minus. And magnesium is a group 2 metal, meaning it forms magnesium 2 plus ions. We need 2 nitrate ions to balance out the 2 positive charge from the magnesium, giving us a chemical formula of Mg parentheses NO3 close parentheses 2. Now we calculate the formula mass by adding the masses of 1 magnesium, 2 nitrogens, and 6 oxygen atoms. The formula mass of magnesium nitrate is 148.33 AMU. Lastly, we have sulfur hexafluoride. Sulfur and fluorine are both nonmetal elements, making this a molecular compound. Molecular compound prefixes tell us how many atoms are present. Since there is no prefix for sulfur, there is one sulfur. The prefix hexa indicates 6 fluorine atoms, giving us the formula SF6. The formula mass for SF6 is calculated by adding the mass of 1 sulfur atom and 6 fluorine atoms, giving us 146.07 AMU. In the laboratory, we are not working with only one formula unit or one molecule at a time. We are working with millions or even trillions of particles. Atoms, molecules, and formula units are far too small to count individually. Instead, we determine the amount of a substance by carefully measuring its mass. This is similar to how produce is sold at the grocery store. Many fruits and vegetables are sold by weight rather than counting each individual item. A cashier does not need to count every grape or green bean. Instead, the total mass can be measured to determine the amount. In chemistry, we use mass measurements to determine how much of a substance we have and how many particles are present. Laboratory balances are not sensitive enough to measure individual atoms or molecules. Our balances measure mass in grams, which is a much larger unit than AMU, used for individual atoms and molecules. For example, a single water molecule has a formula mass of approximately 18 AMU. If we measure out 18 grams of water in the laboratory, we do not have 1 molecule of water. Instead, we have 1 mole of water. A mole is a large quantity of particles. This quantity was intentionally chosen so that the numerical value of the formula mass matches the mass in grams. Molar mass is the mass of 1 mole of a compound. The units for molar mass are grams per mole, or grams divided by moles. Molar mass is calculated the same way as formula mass by using the average atomic masses from the periodic table. The numerical value of formula mass and molar mass are the same, but the units are different because they describe different scales. Formula mass describes the mass of a single particle in AMU, while molar mass describes the mass of 1 mole of particles in grams. For example, 1 molecule of sucrose has a formula mass of 342.30 AMU. 1 mole of sucrose, or table sugar, has a mass of 342.30 grams. The molar mass relates the mass in grams to the quantity in moles. So the molar mass of sucrose is 342.30 grams per mole. Because the units of molar mass have a division symbol in the unit, this quantity is used as a conversion factor in dimensional analysis. Let's work through an example problem. How many moles are in 59.81 grams of CO2? The starting value has units of grams. Whenever you see grams or you ask to find mass in grams, you should think about using molar mass as a conversion factor. First, calculate the molar mass of CO2. Carbon dioxide contains 1 carbon atom and 2 oxygen atoms. 1 times 12.011 grams per mole plus 2 times 15.999 grams per mole is equal to 44.009 grams per mole. Next, we use dimensional analysis to convert from grams to moles. It is helpful to include both the unit and the chemical formula when showing your work. We begin with 59.81 grams of CO2. To cancel the grams, we need to place grams of CO2 in the denominator of our conversion factor. Molar mass is 44.01 grams per mole of CO2. We place that in the denominator so that the grams cancel and we are left with moles. 59.81 grams of CO2 is equal to 1.359 moles of CO2. This answer makes sense because our starting mass is greater than the mass of 1 mole of CO2. So we should have more than 1 mole. Here are some practice problems. First, calculate the molar mass of Prozac, C17H18F3NO. Remember that molar mass is calculated the same way as formula mass, using the periodic table. This compound contains 17 carbon atoms, 18 hydrogen atoms, 3 fluorine atoms, 1 nitrogen atom, and 1 oxygen atom. Since we are working on the mole scale, the units are going to be grams per mole instead of AMU. The molar mass is approximately 309.32 grams per mole. It is acceptable if the last few digits vary slightly, depending on the periodic table used. For the second problem, we are asked to find the molar mass of a compound if 0.218 moles has a mass of 12.02 grams. Molar mass has units of grams per mole, so we need to divide the mass by the number of moles. 12.02 grams divided by 0.218 moles is equal to 55.1 grams per mole. For the final problem, we are asked to convert from moles to grams. When converting between units, use dimensional analysis. We need to start with 0.482 moles of potassium. Since we need to find grams, molar mass will be used as our conversion factor. From the periodic table, 1 mole of potassium has a mass of 39.10 grams. The moles need to cancel, leaving us with units of grams. 0.482 moles potassium times 39.10 grams of potassium divided by 1 mole of potassium equals 18.8 grams of potassium.